continue. Let me also open the table of content. Okay. If I remember correctly, we are in this section. Okay. Let's see. Okay. Let me open the terminal. Let me check. I think I don't really need content anymore. Previously, I decided to download the PDF one by one, but it looks like using the URL is much more convenient, I guess. Okay, and then this one, right? We already doing this. B1.c. Okay. It is kind of interesting. What the fuck? System call is like, yeah, what is it called? We are copying from, I'm not sure from this one or from the bottom one. Maybe from the bottom one. Maybe this is the one that we, what is it called? That we copy, right? Almost exact copy, but not really the exact copy, because we didn't copy the printf, the one before the fork. Right? Oh no. Okay. What is my internet connection? There's a problem. Okay, wait a minute. Okay. Hopefully I'm not disconnected again. We will see. Okay. Yeah, one of the challenges of doing live stream is that sometimes the internet connection is bad. Okay, anyway, we run this fork, right? And then we kind of copy, if I understand correctly, after we run this or call this system call, copy this process or this instruction maybe, and well, again it is almost exact copy, not really the exact copy of it, because we didn't copy to printf. Right, I think I can show you in this one. Okay. It's because we return 69 in here, but the interesting part is that we still running the child process, like we are copying this into another process, right? And we are printing this one. But for some reason, when I add the return in here, it didn't affect anything. I am still not sure. Guess chapter 5. Okay. What about using exit? Okay, right. Still okay. Maybe the chat might exist, right? If I do this, right? Okay, no warning. I mean, this will become redundant, right? Because we are returning in here. Let's see. Oh. Okay. So we're not executing this. So this is executed, but we cannot see the exit code. Interesting. Okay. Let us understand what happened in more detail in p1.c. When it first started running, the process prints out a hello message, right? This one, this identifier, also known as a PID, right? Process ID or process identifier. The process has a PID of 29146. This one. Okay. Let us okay. 29146. In Unix system, the PID is used to name the process if one wants to do something with the process, such as, for example, stop it from running. Okay. So far so good. Now the interesting part begins. The process calls the fork system call, which the operating system provides as a way to create a new process. To create a new process. The odd part, the process that is created is an almost exact copy of the calling process. That means that to the operating system, it now looks like there are two copies of the program P1 running, and both are about to return from the fork system call. The newly created process called the child, in contrast to the creating parent, doesn't start running at main. Like you might expect. Not the hello message only got print out once, right? Because we put the hello message before the fork call. And in case anyone haven't seen this on the previous session, if we do this, right, we call fork first and then we call the start or hello message in the book, right? The start will be twice rather than only once. So we kind of copy the instruction after calling the fork system call. I'm still assuming. I'm not sure if that is correct or not. Okay. Whether it just comes into life as if it had called fork itself. Itself. Okay, this is the P2.c. Okay, I think the difference is in this one, right? Okay, maybe we can copy that. Chapter 5. Okay. Chapter 5 P2.c. Oh, sorry, not CP. And then, well, we open this. Wait. Let me check. Wait, are we back? Okay, hopefully I'm not disconnected again. Okay. She's sweet. Oh, okay. Alright. And then, well, says wait, heater, okay. W status. Wait a minute. What is W status? If a child has already changed state, then this call return immediately. With null, when we give null. Interesting. We are printing the RC weight. Okay, let me try that. No, okay. Parent of RC weight. I'm still not sure what RC stands for. Is it resource? Maybe, RC weight and also PID. Okay, why not doing this like this, rather than having two bracket, I guess. RC weight and PID. Something like this. Okay, let me read this first. You might have noticed the chat isn't an exact copy. Specifically, although it now has its own copy of the address space, okay, its own private memory, its own registers, its own PC. What PC in here stands for, and so forth. Is it personal computer? Interesting. And so forth. The value it returns to the color of frog is different. Specifically, while the parent receives the PID of the newly created child, the child receives a return code of 0. A return code of 0. Okay, this one, right? I mean, it is, if it is less than 0, we will print out an error. But yeah, I'm not sure if the error gonna be on the copy, right? On the copy process, or in the parent process. Yeah, I'm not sure. I mean, we got the value equals 0 in the child process, right? But in the parent process, maybe we get this in the child process too. I am not sure. You know what? Maybe we can make sure of that. Oh, the RC. Okay. We have to print out the RC. And then, okay, let me reset code. Child ID, maybe something like this. Say PID. Okay. RC. Maybe something like this. Zero PID. Okay. So maybe the possibility is that we print out this one in the child process rather than in the parent process, because again the RC in the parent is the process ID or process identifier of the child process. Okay. The value it returns to the color of folk is different. Specifically, while the parent receives the PID of the newly created child, the child receives a written code of 0. Okay, here is the information. The parent receives the PID of the newly created child. The child receives a written code. Oh, so maybe RC mean written code other than resource. Maybe okay. You know what? Written code. Let me print this in here. Okay. This is the process ID of the child, right? And this is the written code of the child. Okay. This differentiation is useful because it is simple than to write the code that handles two different keys as above. You might also have noticed the output of P1.c is not deterministic. Oh, when the child process is created, there are now two active processes in the system that we care about, the parent and the child. Assuming we are running on a system with a single CPU, for simplicity, okay, then either the child or the parent might run at that point. The child or the parent might run at that point. In our example above, the parent did enter print out its message first. Okay. Did enter print out its message first. In other cases, the opposite might happen, as we saw in this output trace. Oh, in other cases, the opposite might happen. Okay, interesting. The CPU scheduler, a topic we will discuss in greater detail soon, determine which process run at a given moment in time. Because the scheduler is complex, we cannot usually make strong assumptions about what it will choose to do, and hence which process will run first. This non-determinism, as it turns out, leads to some interesting problems, particularly in multi-thread programs. Hence, we will see a lot more non-determinism when we study concurrency in the second part of the book. Wait, I think instead of P1, maybe this should be P2, Maybe. But yeah, the print message kind of different. Let me check. Okay. Let me compile this. No, okay. P2. Right. The child is print out first, and then the parent. Something like this. RC, wait. Okay. The RC width is the PID the process ID of the child. So if I understand correctly, waiting for the child process to finish first. I mean, I'm not really sure if that is correct or not. But yeah, what W status in here needs to be suspend execution of the calling thread until one of its children terminates. Okay. What is with PID? ID type, then the ID. Oh, sorry. I'm reading this, not this one. Okay. PID, okay. Nullable W status and then option. System call suspend execution of the PID. System call suspend execution of the calling thread until a charge specified by PID argument has changed state. By default, wait PID waits only for terminated children, but this behavior is modifiable via the option argument as described below. The value of PID can be -1, meaning wait for any child process whose process group ID is equal to the absolute value of PID. Less than -1, equal to the absolute value of PID. If it is -1, waiting for any child process. If it is 0, meaning wait for any child process whose process group ID is equal to that of the calling process, or there is process group ID is equal to that of the calling process at the time of the call to wait PID. More than 0, meaning wait for the child whose process ID is equal to the value of PID. Whose process ID is equal to the value of PID. Okay. So when we use wait system call, which is equivalent to this wait PID system call, we are using -1 as the PID, and then W status and then option. The option is 0. Okay, this is the PID, this is W status, which I'm still not sure what it means. And this is the option. What is option 0? Is an OR of 0 an OR of 0? Or more of the following constant. Yeah. What does this mean? An OR of 0. Is it 0 value? Maybe the following constant, right? For Linux, only option C below. Okay. If W status is not null, wait and wait PIT store status information in the in. Information in the in to which it points. This integer can be inspected with the following macros, which take the integer itself as an argument, not a pointer to it, as is done in wait and wait PIT. What is the return value? PIT, right? Okay. Store status information in the in to which it points. This integer can be inspected with the following macros. Let's take the integer itself as an argument, not a pointer to it, as is done in wait. Or we can take the integer value itself, not the pointer to it. Return true. This one. Return true if the chat terminated normally. That is by calling exit or score exit. Exit 3. What? Oh, this is the, I think, the main page. You know, something like this. The standard C library. Return the exit status of the child. Oh, okay. Maybe we can try this out. So, let's say something like this, right? To store the wait status, I guess. Then instead of wait, right, we use wait PIT and whose process group ID is equal. Whose process group ID is equal to the absolute value of PIT. Absolute value of PIT. So is there wait. Was process group IT is equal to the absolute value of PIT? So is group IT process group IT what is it called? Negative value? I mean, from my understanding, right? Wait for any set process whose process group ID or group identifier is equal to the absolute value of PIT, which is less than negative 1. So is the process group ID have a negative value? I am not sure. Quantity of the calling process at the time. Okay, maybe we can try the 0. Or well, for the first time, let's try using negative 1. Like this, okay. Negative 1 and then W status and then what is the option? What happens when we provide 0 as the option? So return if a chat is stopped. Status for trace. Return receive stop is provide even if this option is not specified. Yeah, I mean, when we provide 0 like this, what it means? Maybe nothing, no option, something like that. Well, let's try something like this. LC wait. Wait. I don't think this is correct. Okay, maybe something like this. IT and see wait and then exit. Returning from main, okay. Exit code maybe. I am not sure what the return value of this. Okay, maybe something like this. You know what? Let's see it like this. Type exit code, something like this. Exited. Status, maybe something like this. Let me check if that is correct or not. This is the expansion of the macro. Okay. Well, let's see then. Exit code 1. Or return true if the child terminated normally. So I think 1 in this case is true. Okay, wait, let me check. What is the status? What is the W status here? 0, okay. And now, let me try return 42 and see what happened. What? That got, okay. By returning from main. So the definition of terminated normally is either by using exit or exit system call underscore exit system call, or by returning from main. So even though the status is not 0, the return status or the exit code is not 0, we still treat that as terminated normally. Let me check in here. Okay. 10752. Let me check. Exit code means oh paper. Okay, right. As far as I know, it is the exit code is from 0 to 255. I mean 0 means there is no error. other than 0, it means there is something wrong. There is an error. Okay. Why does that? Okay. I'm assuming this is the interpretation of 42 exit code. Maybe if we use 0, right? Let's find out. The exit code becomes 0. If we use 69, the exit code is non-zero. Okay. Return the exit status of the child. This consists of the least significant 8-bit of the status argument that the child specified in a call to exit or the argument for a return statement in main. Only if WIF exited return true. Should be employed only if okay. I'm still not sure what the terminated non-normally or not terminated normally in here means. Again, if we use something like this, it will still return true, right? Even when the exit code is not 0. Let's try change this. Exit status. Okay. The 42. The least significant 8 bits. Okay, interesting. Maybe this one, right? The least significant 8-bit of this one is 42. Exit code status. Let's swipe this. Okay. Maybe also no, I think this is fine. Right. Then 752. Then the exit code is 42. It is, I think, consistent. Okay. VIF signal returns true if the chat process was terminated by a signal. Oh, okay. Maybe this is what it means to not terminated normally, terminated by a signal. Let me check. Okay. See, it becomes 0 because we are terminated normally, not using a signal. Okay. What happened when we use this? When WIF signal not return true. Let's find out. Check. Oh, it is 0. It is safety is okay. Interesting. Okay. Exit status. Cordam. Okay. That exit code. The LC wait. Okay, the LC wait in here means we are waiting for this type process. Okay, maybe we can try this one, the PIT value. Instead of negative 0, we can try negative 0, negative 1. We can try 0, something like this, and see how it goes. Okay. Don't have any. It's still the same because I'm assuming we are in the same process group ID is equal to that of the calling process at the time of the call to wait PID. Okay, and maybe we can also change this with RC, like if the value more than 0. Now let's find out. Okay. Equal. Alright. Maybe let's use this as an example. Okay. So I put this like this. Okay. Okay. let me commit this. Example of using oh, the explanation is in here. Okay. All right. Of using proxy's call. Maybe I should give some explanation. We are kind of copying the instruction below. After call to fork to another process. That's why it looks like that's why it prints out that's why this will print out the parent and maybe let's only have this, I guess. Okay. And the value of RC so I assume which I assume stands for return code. Will change depends on which process we are currently in. If we are in the parent process, it will print out a value of the child process ID, and if we are in the child process, it will print out the return code of the fork. Let me check. running process is referred to as the parent process. Okay. The child process and the parent process run in spirit memory space. At the time of fork, both memory space have the same content. Memory writes file mapping by one of the process do not affect the other. Okay. The child process in an exact duplicate of the parent process except for the following point. Okay. The child has its own unique process ID, and this PID does not match the ID of any existing process group, okay, or session. The child's parent process ID is the same as the parent's process ID. Okay. The child does not inherit its parent's memory logs. Process resource utilization and CPU time counters are reset to 0 in the child. The child's set of pending signal is initially empty. Does not inherit semaphore adjustment. Okay. What is the PID underscore T? Maybe something like this. Okay. And then an example of using fork system call. A simple example with copying the instruction after the fork call another process. Commit menu edit. Okay. And then alright, let me copy this as a reference. Okay, git commit menu edit, and also this one. Okay. The wait system call. So far we haven't done much. Just created a child that prints out a message and exit. Sometimes, as it turns out, it is quite useful for a parent to wait for a chat process to finish what it has been doing. Parent to wait for a chat process to finish what it has been doing. This task is accomplished with the wait system call or its more complete sibling with PIT. Okay. See figure 5.2 for the tiles, this one. Okay. In this example, at P2.c, the parent process calls wait system call to block its execution until the child finishes executing. When the child is done, the parent becomes unblocked and wait returns in the parent. Adding a wait call to the code above makes the output deterministic. Can you see why? Go ahead and think about it. Waiting for you to think and done. Not that you have to update. It is the output. Yeah. Okay, this one. It is kind of, what is it called? A similar pattern to this one, right? Well, there is some difference. We don't have the RC wait in here, right? That is one of the difference. Okay. Deterministic. With this code, we now know that the child will always print first. Why do we know that? Well, it makes simply run first, as before and to sprint before the parent. However, if the parent does happen to run first, it will immediately call wait. The system call won't return until the child has run and exited. Thus, even when the parent runs first, it politely waits for the child to finish running, then wait returns, and then the parent prints its message. Okay, I'm assuming it becomes deterministic because even though we run the parent process first, right, we can be sure that the parent will wait until the child process finishes. So, what is it called? Preventing risk condition, maybe something like that. Because previously in the P1, there is no guarantee that, what is it called? The child did not finish first before the parent, something like that. So there's a case when the parent finishes first, and there is also a case when the child finishes first. This is when the parent finishes first, I assume. And this one, where is it? This one when the child finishes first. That's why it is not deterministic. I mean, again, this is my hypothesis, which might be wrong. I'm learning to think, Okay. The system call won't return until the child has run and executed. Thus, even when the parent runs first, it politely waits for the child to finish running. Then wait returns and the parent prints its message. Okay. Let me read this first before continuing to this section 5.3. There are a few cases where wait returns before the child exits. Read the main page for more detail as always. And beware of any absolute and unqualified statement this book makes, such as the child will always print first, or unique is the best thing in the world, even better than ice cream. Beware. Again, we are also learning to think about the statement from this book. Okay, so there's also a case where the word written before the child exits. Okay, which main page is that? Which part of the main page is that? Are used to wait for state change in a child of the calling process and obtain information about the child whose state has changed. Is considered to be the child terminated. The child was stopped by a signal, or the child was resumed by a signal. In the case of a terminated child, performing a wait allows the system to release the resource associated with the child. If a wait is not performed, then the terminated child remains in a zombie state. Oh, okay. Not performed, then the terminated child remains in a zombie state. Hold on a minute. Let me make sure again what the zombie state in here meant. Okay. Could be placed in a final state where it has exited, but has not yet been cleaned up. Oh, so we haven't cleaned up the child process. Remain in a zombie state. Okay. Hello. The Kid Coder, welcome. We are currently trying to learn from this book, Operating System 3 Easy Pieces. and currently on chapter 5, this one, and I'm kind of checking this footnote, about the wait system call. Few cases where wait returns before the child exits. Return before the child exits. Oh. If a child has already changed state, then this calls return immediately. Change state, In the case of a terminated child, okay, wait a minute. But the child whose state has changed. A state change is considered to be the terminated, right? Either we are using exit or return in the main function. The chat was stopped by a signal, or the chat was resumed by a signal. Okay, maybe this is the case. When the wait returns before the chat exit, wait system call returns before the child exits because the child state changed, and the change is that the chat was resumed by a signal. Maybe I'm still making a hypothesis. In the case of terminated, okay. See, if a child has changed state, then this call returns immediately. The rest they block until either a child changes state or a signal handler interrupts the call. Assuming that. Wait a minute. Wait. Okay. Am I disconnected now? Okay. I think we are back. Okay. I inspired from this thing. I'm talking about profile picture. I'm inspired by this thing, but I don't. What is it called? I'm not trying to mimic his profile picture, I just find some simple profile picture. I just like a simple profile picture, something like that. Okay. Wait, PIT. To keep in mind that this function might return before the child process exit. ID might wait a minute. Hold on. Okay. Am I connected? Okay. Yeah, my internet connection kind of have some trouble. Okay. Migrate before the site process exit the main page. Where is it? The wait function. The system call will return. Subscribe, get content, get going. Thank you to Kit Cutter. Okay. The system call will return immediately if the chat process. Okay, maybe this before process exit. If the chat process change state, including resume process by a signal. Okay. The system call will return immediately if the chat process by a signal. Alright. Okay. On Linux there are 6 variants. Oh, we are already in this section. Okay. Let me commit this. Git commit. Okay. Use fit. Yeah, maybe I should use for the feature. An example of using wait system call. Oh, not really with IT, because yeah, we are not really using the wait function, but we are trying out the wait PIT instead. Let me check. Okay. Okay. An example of using for this is a simple of using PIT to wait the type process we're waiting the chat process this one. Return 42. Okay, the return before already finished, I guess. This or maybe terminated. The return before continuing the parent process, something like this. Okay. To return first, something like this. First before continuing the next instruction. Okay. Alright. Okay. Let me do this instead. Commit amend, no edit. No, let's check this one. Okay, for continuing to add the next instruction. Return immediately if the chat process changes state, including resume process by a signal. And not only when chat process what is it called? Exit. Change state encoding resume process by a signal. Not only when the chat process finishes, but also when maybe something like only when the chat process finishes, but also when chat process resume by a signal, something like this. But also when the chat process resume signal. Okay, alright. Let me. And I didn't commit another file, right? Okay. Just making sure again. Alright. Or maybe I should commit this too. Add toolkit ignore the binary or executable, I guess. Executable in the directory. But not the source code. Okay. The exec system call. I think we will continue this on the next session. Again, my internet connection is having some trouble, so I'm not sure if I'm gonna disconnect it again. So let's end this here. That's it for now. Thank you for watching and see you next time. Bye bye.